Here comes example number 1. What in this example, we go back to volume of solid of revolution. We need to rotate the region bounded by the following. Okay, we have a y equal inverse tangent of x, y equals 0, and x equals 1. And we rotate it about the y-axis. Of course, we want to find the volume of the solid of revolution. Okay, so we have that function that is the inverse function of the tangent, and then we have the line y equals 0, in other words the x-axis, and a vertical line x equals 1, and we rotate it about the y-axis. So let's sketch the function and the constraint and see what kind of volume of what kind of solid of revolution we create by doing so. Do you recall the graph of the inverse tangent? It's like the tangent, but you lay it on the side, right? Remember, what is the domain of the tangent is negative pi over 2 to pi over 2, and that will be the range of the inverse. So we'll go from, let's say, this will be pi over 2, and this will be the top asymptote, the horizontal asymptote on top, and at the bottom we'll have y equals negative pi over 2. Okay, now the function as we approach, I'm looking back at the tangent, as the tangent approach pi over 2, I'm sorry, as x approaches pi over 2, the tangent goes to infinity. So again, reverse or swap x and y here. So as the inverse goes, the input of the inverse goes to infinity, then the inverse will go to pi over 2. The graph is going to look like this. Okay. Now, what happens when x equals 1? That's the other line that we part of the constraint. When x equals 1, then you have the inverse tangent of 1. Well, the function that the input for the tangent that creates the tangent that equals 1 is pi over 4. So the intersection between the line x equals 1 and the inverse tangent is happen at y equals pi over 4, like so. Okay, so this intersection is 1 comma pi over 4, and now this is the region that is bounded by the curve, by the line y equals 0, which is the x-axis, and by the line x equals 1. So we're looking at this region right there, and we rotate it about the y-axis this way. Okay, so as we rotate this region, it comes, the other side is right here, and let's see, it looks like that, and the volume is this shape. Okay, so this is the volume This is the solid, I'm sorry, I keep saying the volume, but this is the solid of revolution. And because of the cylindrical shape of the solid, it stands to reason to use the cylindrical shell technique. Okay? So, by the cylindrical shell technique, or shell method, remember, for the cylindrical shell, we need to have the circumference C, the height H, and the thickness T. So circumference C equals, well, in this case the radius will be x, so it will be simply 2 pi x. The height of the function h, well, that will be the inverse tangent. So it will be the inverse tangent of x. And the thickness, t, is simply dx. And the volume will be the integral where we can pull out the 2 pi. The integral x goes from 0 to 1, x inverse tangent of x dx, like so. Okay? So, at this point, what we could have done, if we didn't have a table, we could have gone through integration by part, because this is a case where you have a simple algebraic function x, or if you want, it's a polynomial of first degree, multiplied by a transcendental function. The inverse trig function is transcendental. And when we went through different strategies, we said that one of the cases where we will use integration by part is when we have a product of a transcendental by non-transcendental, by algebraic or such as a polynomial function. All right? But the topic says integration using table. So you have the handout, and at this point we need to look at the table and see which one will provide this integral, x tangent, the inverse tangent of x. And if you look at the reference tables or reference pages, and this is, by the way, is at the end of the book. You have those, as well as other resources. Integration start on the second page. You can see that we have a whole lot more integration tables than differentiation. And the group that contain the inverse trigonometric will follow the trigonometric. So you can see that 63 to 70 to 86 are the trig, and the inverse start from integral number 87 and end up with integral number 95, I believe. Indeed. So, so that will be the group where we're going to look it up, 87 to 95. And did you find a matching integral? Something multiplying the inverse tangent? 92. By formula 92. So let's see what we have in formula 92. Formula 92 read the following. The integral of u inverse tangent of u du equals to u squared plus 1 over 2 times the inverse tangent of u minus u over 2. And then we have to add the ever-present c. Okay, so what we need to do is just convert this formula to our needs. The conversion is straightforward. Here we have only u being converted to x. So by this, actually, I can write it at the bottom here, as we are done. So No, actually, it's a definite integral, so I need to do more than... so in our case, we're going to say that v is 2 pi, the integral actually I'm going to just multiply 2 pi by the result of the integral from the table. So just we'll replace u with x. So we have x squared plus 1 over 2 inverse tangent of x. Minus, hang on a second, minus x over 2, and we need to evaluate it from 0 to 1. Okay. Okay, so now let's evaluate from 0 to 1, then I'll answer your question. So, let's see, 2 pi, we start with 1, and we have, well, 1 plus 1 over 2 is 1, so that's taken care of. What is the inverse tangent of 1? Folks, this is a question for you. Pi over 4. The tangent of pi over 4 gives you 1. So we have pi over 4, and here we have minus 1/2. And I think that's it, because if you look at 0, well, the inverse tangent of 0 is 0. And, of course, 0 over 2. And all we need to do is simplify here. And we have pi squared over 2 minus pi. And this is the volume of the solid of revolution in our case. Okay? So, this is the end of this particular example. And I'll answer your question next. The question was, I assume that you were interested to know if you'd be allowed to use this table in the test. You're not expected to memorize 147 or so integrals. I can tell you that much. Whether this will be allowed in the test or not, it remains to be seen. In the past, I did not use this section in the test. It was for your own benefit, because from this point on, you can refer to the table as you solve integrals. Except the test, you need to demonstrate your ability to solve integrals. In reality, every one of the 147 integrals, I assume there are 147, I think that's the number I heard from you guys. Whatever the number, you have enough knowledge. What we learned so far in terms of integration technique gives you enough power, brain power, to produce each one of these integrals. So the intent of this table is to save you time as you continue, as we start applying integration technique. We go into the application. So you don't have to reinvent the wheel. An example where you can use a result that you already know is if you run into a solution that requires the integral of the secant. Now this is not a trivial integral, but since we already done it, and you know what is the solution, what is the integral of the secant, you can just write in the answer, which is, of course, the natural log of the absolute value of the secant plus the tangent. Okay, the other cases is the integral of the tangent, the integral of the cotangent, the integral of the secant. You don't have to resolve it every time. It's okay, we've gone through that, we know how to do it, now we're going to apply it. From this point on, when you run into a need to solve an integral, except for the test, but as you do your work, you can refer, okay, this is formula so-and-so. And that's what we're actually going to do for the next 3 or 4 examples. All right? So that was the answer to your question.